शेयरिंग नहीं हुआ है सर.
शेयरिंग ओके. Is it visible now?
ये डुप्लीकेट से.
इसमें क्या करना है? ऑलरेडी शेयर ना, फुल स्क्रीन. Not visible?
It's okay, but projector, your entire screen.
Oh. हाँ. Now it's totally right. Is it fine now? Okay. Okay. Sorry for the trouble. I think we are delayed by 15 minutes. Okay. So let's start the today's session, which is day 8 and lecture number 15. So I'll be discussing about the vibration-based structural health monitoring and role of Bayesian method in SHM. So till now you have been exposed to only theoretical lectures, and many methodology related to AI and machine learning have been discussed, and many illustration have been also carried out. However, the real-time application or some actual problem of structural health monitoring related issues have not been discussed in detail. So today I am going to cover those things, the practical aspect of how to implement structural health monitoring and what is the need of Bayesian method in it. So those things will be discussed. So as you know, probably this background have been already discussed by our foreign expert, Dr. Susmita Naskar. So why structural health monitoring is needed? In the introductory remarks also I have said that there are a lot of development projects that is going on as part of our Viksit Bharat project, right? So many infrastructure is coming up, and as a developing nation we should develop as many infrastructures as possible, right? Also, if you go to any developed country, you will see their infrastructure is huge. Okay, the number of roads, number of buildings, number of bridges are significantly higher than what we are having in India. Okay, so to become a developed nation, we need to develop a lot of infrastructure, and those infrastructure actually acts as a socio-economic development of any country. So whether you are developing nation or not, that depends on your infrastructure. Okay, because if you build more bridges, more roadway, highway, railway, then your logistic or business will be also higher compared to your earlier period. So that is the main reason that we need to develop lot of infrastructure. And the thing is that the developing infrastructure is not the end of the goal. Now this infrastructure takes lot of time and also lot of money. Okay, because lot of budget has been sanctioned for developing this infrastructure. So these are the important asset of any country. So we must need to preserve this important infrastructure. Otherwise, there will be loss of economic losses will be there, or human losses will be there. Because if there is a catastrophic failure, then there would be human life losses or some other property losses. So there will be huge economic losses related to it. So we must need to preserve this. Okay. Sorry. So let me probably. What is happening? I don't know. Keyboard. Yeah, it is working fine. So, as I said, lot of highway, railway, bridges, those things need to be constructed, and then they need to be maintained over the period of time. Okay, once they are constructed, you should not leave them. Okay, you should also monitor them. So what happens in India particularly, there is a reluctance or negligence from the government side or bridge maintenance owner. Okay, so that they don't usually maintain their infrastructure regularly. Okay, as compared to other developed nation where the periodic maintenance is rigorously done, and they also have inbuilt sensor installed in all the new infrastructure. So that is missing in India. However, there is a huge effort now going on to apply such type of maintenance system or monitoring system in Indian bridges. Also, we have a large stock of historical building or some old stock of bridges, right? Many railway bridges are more than 70, 80 years old. Okay, still they are running. So we need to not only preserve those infrastructure, but also we need to enhance the capacity, because day by day our capacity or demand on the same infrastructure is increasing, because we are enhancing the traveling speed, for example, or number of vehicles are increasing day-to-day basis. So we need to cater to those demand. We need to enhance the strength of the existing infrastructure. So what happens over the period of time, you will see there are a lot of corrosion, fatigue, collapse, or because of the natural disaster. These are unavoidable kind of corrosion. Corrosion will occur whenever there is a moisture in the air. Okay, so what you can do at best, you can apply corrosion resistance paint in the structure periodically. Okay, and then fracture is usually caused by live load, which is also unavoidable. It will always occur, but thing is that you should have a monitoring system so that you can detect the crack much well in advance than the final stage related to the collapse of the entire structure. Okay, so those things could be avoidable if you have in-house maintenance system or inbuilt maintenance system. And then flooding, of course there will be flooding, but of course in developed nation there are also flooding prevention system. In Tokyo, when I was there, so I visited underground tunneling system. Okay, just for flood water, okay, management. So they have built lot of huge infrastructure underneath the ground. So in the time of this huge rainfall related to flooding, so they actually open the gate and then divert those collected water to the sea or ocean directly. Okay, not to the river. So if they divert this to river, then the river will flood and then eventually the nearby area will be inundated. So those type of system could be developed at least in metro cities. As you hear from time to time that in Mumbai, always during rainy season there are a lot of flood is happening and people are fading up with this problem of commuting from one place to another place during rainy season. So earthquake also a very natural common phenomena that is occurring in many parts of India, especially to northeast part of the India. Okay. So what we need to do, we need to have a maintenance system to predict the life of this infrastructure and also to have some understanding about the performance of existing infrastructure, how they are performing. If there is a damage, then when it will occur, okay, and then if it is occurring, then we should able to detect those, okay, and then we can use preventive maintenance system, okay. So these are the things. So these call for a attention of civil infrastructure management owner because these are the, as I said, these are very important infrastructure and we need to monitor them, and because of the natural degradation or also the environmental factor, the damage is bound to occur. So this causes a global infrastructure crisis, okay, and to solve this crisis many researchers from all over the world came up with the idea of doing the or applying the maintenance system on the structure, similar to monitoring the human health. So suppose we are having some issues, there is some problem with your body, then what we do, we go to the doctor and doctor prescribes something, okay, and then probably blood test is prescribed, and then we go to the clinic and give the blood sample, and from the blood sample we try to extract some features like blood count, platelet, and or liver function. So those are the kind of signature of human body which tell us that how our organs are functioning, right? So similar things could be implemented with the structure as well. So what we do, we will install some sensor on the structure and then monitor response from the structure. From the response, then we have to determine the health of the structure. So because there is no other way we can detect any kind of anomaly or deterioration or damage in the structure, right? So we need to rely on the response from the structure only. Based on the response, we should detect. Similar to human health, okay. So this researcher that they are working to solve this global infrastructure is this methodology is known as structural health monitoring, okay. So our objective is to prevent the catastrophic failure, also detect the damages in advance, and then we should suggest a maintenance system that will lead to efficient management of the infrastructure, and also it will help us to reduce the maintenance cost, okay. Because if you go for manual inspection, of course you can go for manual inspection, but manual inspection is subjective, depends on the expertise of that individual person. So if the person is very expert, he could able to detect the damage, but if the person is not expert enough, then probably he or she will miss some point that is critical to the structure, right? So also if you go for manual inspection, that is also very much costly because you have huge number of infrastructure. So probably you need to recruit lot of manpower. So it is not a logical way to do. So the most logical way is to have some monitoring system. You place the sensor, and from the sensor you collect the data, and from the data you try to infer the all the information that is necessary to assess the health of any structure, right? So these are the objectives that we need to fulfill using the structural health monitoring, or the title of course here is the sustainable structural monitoring. So our one of the objective is prolong the service life. So just by implementing an efficient management system, we can do the maintenance at a certain interval that best cater to that particular structure, right? So in that way we can also prolong the service life, okay, by doing the maintenance of the infrastructure periodically, and then we can also minimize the downtime. Okay, if you don't have any health monitoring system installed in a structure, then what will happen? One day the structure will collapse, or before collapsing probably there will be major damage, and if there is a major damage, then you need to go to the site and repair them. So that will cause obstruction of the use of that structure. So we don't want to want that thing to happen, because we want our system to be in service all the time, right? So to minimize that, what do we need to do? We need to install the sensor, and then we need to get the data real time and monitor those in continuous way, so that before happening any major damage, we will have this type of alert system, or some kind of maintenance scheme can be developed, so that we can prevent the major damage in the structure, right? So that will help us to minimize the downtime and also avoid the catastrophic failure of those infrastructure. Then this will lead to decrease in overall maintenance cost. Okay, once you are applying some maintenance scheme using limited number of sensors, and it is efficient enough to detect the damage in all entire structure, then it will of course lead to lower maintenance cost as compared to your manual or visual inspection. Okay, then it provides the improvement in design and construction. How it provides? Because now you have inbuilt sensor, okay, installed in the structure. So from the sensor you are getting the data, right? So you know how the system is performing now. Okay, so you can compare with your design drawing or design or numerical model. Okay, from the numerical model you can also come to know what is the performance of the structure, and you can compare the actual performance of the existing infrastructure and the performance that is supposed to be there from the numerical model. So if you are seeing some deficiencies there in the actual structure, then you can propose some modification in your design, so that further improvement could be done for new construction or new design, right? So this will not only help for maintenance but also to improve our understanding about the structure. Okay, so let's go to the next slide, which is structural health monitoring and overview. So now the thing is that I have mentioned what is the need of structural health monitoring. So next thing is important is how to implement it, or how we can detect or achieve those objectives that I have discussed just now. So what happened? Whenever there is a structure is constructed, their intrinsic property, means natural property, is changing over time. Okay, so that happened because of the environmental factor as well as the load that are subject to the structure. Like the bridge is subject to tremendous amount of live load. So because of the live load, there is a fatigue damage. Okay, so not only environmental but also fatigue damage. Now what do you understand by damage? What is happening because of the damage? Could you tell me, just to understand whether you are able to follow what is damage actually to the structure and what damage changes to the structure. Okay.
This is reduced.
Okay. Yeah. Any other? Yeah. That is a good point.
Serviceability properties will change.
Yes. So apart from stiffness, is there any other property that may change over time because of the damage? Yeah, before modal property are related to physical property like stiffness. So any dynamic system, as I said all the time to my undergraduate student, that any dynamic system can be repeated by 3 parameters. Essentially 3 parameters are needed. Okay, those are coming from physics if you see, because one parameter is mass, right? Always there. Any system, not only civil engineering, you think about anything, even you can think about yourself. So whatever object is there on earth or beyond earth having some mass. Okay. So inertia is there always, right? Any other thing is there? Yeah, damping means energy dissipation, always occurring. Okay. Whether it is frictional energy dissipation or air energy dissipation because of dragging. Okay. That is also friction, but there could be internal energy dissipation also. In terms of structure, you can see there are a lot of joint and member is there now. So in molecular level, there is also molecules are connected to each other. So when there is a vibration, so as a whole it is vibrating and there is an internal friction also developing. So we call it internal energy dissipation, and then there is a external energy dissipation. Okay. So those are damping. Any other thing? That is stiffness. He has already suggested, because stiffness is always there, which acts as an energy storage device. Like damping acts as an energy dissipating device. So there must be something which acts as an energy storage device. You might have wondering, like you are holding a rubber, stretching it, right? So then you are releasing from one end. So what will happen? The rubber will come back to its original position. Now how? It is a non-living thing, but still it is moving. So that is the thing, that when you are stretching the rubber, the elastic property or spring inside the rubber acts as an energy storage device. As you know, strain energy is half of K U square, right? K is there, no stiffness. So that acts as an energy storage device. So whenever there is a force that is you are applying to make deformation of any structure, so there is a storage of energy as well as dissipation of energy that is occurring simultaneously. Okay. So the damage means there is a change in any of these physical parameters, whether mass is changing over time or stiffness is changing over time or damping property is changing over time. Okay. So any of these property could change. So for example, as I mentioned in the first slide, damage is related to the corrosion or fracture or fatigue and so on, right? So they eventually means, suppose because of the corrosion, what is happening? The member is corroded, means its property is getting changed or thickness is getting changed, right? So if thickness is getting changed, then stiffness will change, because you know the formula of stiffness, right? So there will be in the stiffness formula there is not only material property, there is a geometric property also. L is there, P is there, B is there, okay, because I is there, na, in a moment of inertia is there, okay, BdQ by 12, okay. So those things is there. So all the things are taken care of by stiffness. So if there is a reduction of thickness or reduction of material property, there will be reduction in stiffness, okay. And then there could be change in boundary condition also. Okay, for example, there is a bridge, then there is a roller support. So over the time, roller support could become very stiff and becomes a kind of pin type support. Okay, or there is a joint which is designed as a perfectly pin for truss bridges. It's kind of pin or hinge. Okay, so but they are not perfectly pinned. They are bolted in real side. Okay, so those things can be rusted. There could be degradation of those stiffness component, okay, as well. So there could be change in boundary condition as well. So damage essentially means change in these three parameters. One is material property, geometric property and boundary condition. Now when there is a change of all of these or any of these, there will be change in K or mass or damping. Okay, now you have to look into those aspects. How to detect those changes in stiffness or in mass or damping. So that is the challenging thing. So okay, so now you come to know what actually damage does to the structure. Now the next objective is how we can detect the changes in those parameters. He has suggested a modal parameter. Of course, if you understand the dynamics of structure, then there is a Eisen equation. So the Eisen equation is governed by the modal parameter, and there is a link between modal parameter and stiffness and mass, right? If you solve the structural dynamics problem. So what happens? You will install the sensor on the structure, and from the response of the structure you have to identify the changes in the response of the structure, right? So in the measure response there could be strain, there could be displacement, there could be velocity, or there could be acceleration, force, temperature, based on your actual problem, okay, what you are going to study, right? So then from this measurement, for example, I have shown a time history acceleration of acceleration, measure acceleration, okay. So from this response, any of these, then I have to detect something that is related to the physical parameter of structure, okay. So what are those? This process of detecting the features is known as system identification, okay. So detection of natural frequency or mode shape or damping parameter or any other thing. Not only this, but you can directly correlate also the measure response. Suppose you are measuring a response from a healthy structure, so-called healthy is not known to you, it could be unhealthy also, okay. So for example, probable healthy structure and then probable unhealthy structure, you can directly compare their measurement also, if possible. But direct comparison measurement is not feasible because it does not give you the fundamental parameter related to the structure, right? So acceleration, suppose you are measuring, so acceleration is not directly linked to the fundamental parameter. Acceleration could be changed because if you are moving a lighter vehicle, acceleration will be reduced, right? If you are moving a very heavy vehicle or traveling speed also, if you increase, then acceleration on the bridge will increase. So those are not a parameter to be compared, right? So what you need to compare? The fundamental thing like natural frequency, mode shape or damping or some other features, okay, that you need to figure it out. If there is no changes in all of this, then what you need to do? You need to look for another features, okay, you keep on trying. Then the third step is damage characterization. What do you mean by damage characterization? Damage characterization is the process of identifying the damage in the structure. Now if you able to identify the damage, then you have to also identify what is the type of damage, okay, whether it is fracture, whether it is corrosion, whether it is some other. Then you also need to identify whether what is the extent of damage, means damage severity, or also the location of the damage, where the damage is located, because unless you don't know the location, how can you do the maintenance or, right? So detecting damage is one part, but there is other several part also, okay. So you have to detect the location, you have to determine the severity, you have to determine the type of damage, okay. Then based on the extent and type of damage, you have to also estimate the remaining life or residual life of the structure, okay. So once you have all of this information, then what you need to do? You need to then take a decision whether the structure to be demolished. If the damage is significantly large, then you have no choice but to demolish the structure. Whether it could be retrofitted, it could be repaired, so that decision comes next, okay. So these are the 4 goals of structural health monitoring, okay. You always remember this thing, this is the fundamental thing, okay. Now we have to achieve all of this, okay, to implement a real-time structural health monitoring. Otherwise all the talk that we are discussing like AI and machine learning all will be in vain if you could not able to obtain these 4 steps, right? So to obtain or to execute these 4 steps in structural health monitoring, what we can do? We can implement a vibration based damage detection or vibration based structural health monitoring system. So idea is to detect the changes in the structural responses or parameter from the measured vibration response, like acceleration or displacement or velocity, whatever it is, okay. Just you are placing some sensor and measuring the vibration of the structure, and from there you try to obtain all of these 4 steps. So what are the challenges? So this methodology is not so easy to implement. The challenges are practical challenges I am talking about. One is the sensitivity of modal parameter. I have said now over here the feature extraction. So there are modal parameter like frequency, mode shape, damping. So if they are not sensitive, suppose there is a large breeze, okay, and there is a small crack at the end of a diagonal member. Diagonal member, probably some diagonal member are tension, and when it is tension in steel, there is a chances of fatigue damage or fracture damage. Okay, so suppose there is a one damage in one member of the entire structure, so that is a local damage, and because of that damage, whether there is a change in modal parameter of global modes I am talking about, because you are placing sensor at a relatively few points. Okay, you have a limited budget, you can purchase only probably 6, 7 or 10 maximum sensor, not more than that, and you have a huge structure. Now using those sensor, your objective is to identify the global parameter of the structure, not the local. If you want to identify the local parameter, then you have to place the sensor at every member of the structure, then only you can measure the local response, right? Is not it? So the problem is, because of that small damage in one of the member, will there be change in the modal parameter of the entire structure? That is a question. Okay, so of course there are some examples where there is a changes in modal parameter because of the small damage in a structure. Also there are some examples where you cannot identify the changes in the global parameter, okay, of global modal parameter like frequency, mode shape or damping. Okay, so then the question is, then how can we detect damage? Because our detection procedure highly relies on the modal parameter, which are the fundamental parameter. So if there is no changes in those parameters, then how can we detect damage? Okay, so that is the challenge. So you have to see first whether conventional method on the modal parameter are working or not. You have to check. If the modal frequency are not sensitive, then you go for mode shape. Then if directly mode shape is not sensitive, you apply some other method based on mode shape like MAC or modal curvature or some other thing related to mode shape. Okay, try to enhance the sensitivity. Okay, and then you go for also damping. Sometimes damping is highly sensitive because it relates with the energy dissipation. Now when there is a damage, it is expected that energy dissipation also increase. Okay, so there could be changes in the modal damping ratio. But problem with damping is it is also not kind of stable parameter. Okay, it also depends on the amplitude of the vibration. Okay, if it is frictional, then it depends on the, because you know Coulomb's law of damping, these are all elemental now in physics, Coulomb law. So there is amplitude term is there. So if there is an amplitude term, so higher vibration means higher amplitude, means higher energy dissipation. So damping will be higher. Okay, so you have to also check whether the damping increase is happening because of the increase in amplitude or because of the actual damage. Okay, so those things you have to rigorously check and investigate. Okay, so as a researcher in this domain, you must have the ability or expertise to understand the changes of physical parameter because of the actual damage or because of some environmental changes. Okay, and of course I am also coming to other part, that is the measurement part. Of course the measurement is not absolutely correct. There is a noise also in the measurement. So you have to also screen out the noise part. So those will be discussed in subsequent slides. Another is the limited number of sensor available. As I said, you cannot place sensor at all the point. Okay, you only place sensor at a limited location, right? Yes, you want to ask something?
Sir, to check whether how, what is the change, what number of, sorry, to check the change in modal characteristics like frequency or damping or whatsoever, there it is always mandatory to have some base structure. So we have like
Yeah, that is a good question. That is the next point of discussion. In the next class, I will address your question. Okay, so just wait. And then measurement noise and modeling errors are there. partly his question is if you want to compare with your measurement, you have to compare with something. So baseline model. So then baseline model is also having some modeling error, and measurement also having some measurement error. Then how to eliminate all of this? Okay, that will be discussed in the next slide. Okay, that is a very relevant question, and always we are having this type of thing in structural health monitoring. So you cannot have only measurement, you cannot have only numerical. So those who are working in structural health monitoring have to take care of both the things, like experimental, also numerical. So what is happening? The physical system, once it is constructed, then only measurement is possible. Before it is not constructed at the site, how can you take the measurement, right? So it exists as a numerical model before construction. Suppose you are planning to construct a new structure. So you are designing a structure, then you are performing a numerical, you are constructing numerical model, and then performing some analysis. Okay. So from the analysis you are getting some modal parameter or time history response, whatever you are want to evaluate. Okay. So that is the numerical model, right? So that could be your baseline because it is based on your design parameter. Now, when it is constructed at site, then only measurement is possible, right? Now the thing is that civil engineering structure are constructed manually at site, not like mechanical engineering where machine is manufactured by robot, okay, and it is manufactured at a mass scale level, okay. So civil engineering structure always constructed one at a time or at the site by manually, right? So what is happening? It depends on the workmanship of the skilled labor. Okay, whether if the labor is very skilled, then dimension will be as per the design. Sometimes you will see the framework is going here and there, so dimension is not as per the design, right? So if you work in the construction site, you will get to know. Okay, so there is a deviation of dimension. Then there could be deviation in reinforcement, because theoretically I am giving this reinforcement like this, there will be some overlapping was there, and there should be another kind of extra reinforcement should be there. But at site, it could be possible that it is not implemented correctly. Okay, to minimize the cost also from the contractor. Then there could be a discrepancy between the design and the actual implementation. Also, you are making the concrete as a batching plant probably, and then transported it to a site where you want to pour the concrete. Now there could be deviation of the strength of concrete as well. So there is a lot of variation that could be possible in case of civil engineering structure. So what is happening? None of this numerical model or this measurement are correct or perfect. So why not perfect? Whatever, suppose you are making a structure, whatever it is constructed, that is the final. Okay, you cannot again go back and change anything, right? So that is your final. So you should rely only the existing structure, and from the existing structure, the response that you are getting, that is the final response. Okay, so then you don't need to trust on the design or numerical model. Okay, because numerical model was the initial kind of model based on the design parameter. Now when the structure is constructed at the site, there could be lot of changes. Okay, so that is your final thing. So all the evaluation should be based on that only. Okay, now the comparing part, of course there is you need to compare with something, because initially you have nothing. For example, once it is constructed, also whether the structure is healthy or not, how to know? Because there could be, as I said, there could be discrepancy in the lot of things, material property or some detailing of the reinforcement. Okay, so if someone asks you whether the constructed structure is as per design or not, whether it is matching the expected response or not, then what you need to do? You need to compare with the numerical model. No? The numerical model also have certain limitation, because you are constructing numerical model based on various assumptions, like choice of element. Okay, suppose a beam is there, you can model the beam as a 1D, 2D, 3D. Okay, you can use Timoshenko theory, you can use Euler-Bernoulli theory. So there could be a lot of assumption. So based on those, you can have defined numerical model. So what is happening? So there are modeling error in the numerical model because of the choice of element or the boundary condition. As you know, there is no perfectly pin joint, perfectly fixed joint. You cannot make, okay, in reality. Those are on theory only, okay. And then material property, modeling of joint material property also you are assuming something, and at the side there is something else. Okay, because of this there is some modeling error, and in the measurement also there is some measurement error. Okay, because there is a self noise of the sensor, there is a ambient vibration of the structure because of the wind or natural vibration of the structure also there is some ambient. So all of these need to be taken care. Okay, so that process is called finite element model updating or data assimilation. Okay, so you have to rely on the existing structure, whatever response you are getting, that is the final thing, because you cannot change the structure once it is constructed. So based on the response, then you have to update your numerical model, is not it? So numerical model, suppose you are performing the model analysis in the numerical model, you are getting certain frequency, and then you are testing the structure on the side, taking the acceleration. From the acceleration you are also performing system modification using some SSI or ERA method, and then you are getting some model parameter. Okay, so if there is a discrepancy, then both are not same. So you have to make your numerical model so that it represents the actual structure. So you have to update it, okay, based on the response from the actual structure. So that process is called data assimilation or finite element model updating. Now as I said, because there are modeling error, also measurement error, so that means these are uncertainty into the model or measurement. So those uncertainty has to be treated before you develop some methodology. So how to treat that? That is the domain of Bayesian model updating. Because those are uncertainty, they need to be quantified. So to quantify any uncertainty, what method will we use? Probabilistic method, right? Statistical method you have to use, because otherwise you cannot quantify the uncertainty. Any other method you cannot quantify. There will be uncertainty but cannot be quantified. Okay, suppose least square method you are using. Okay, you are just minimizing the error but not able to quantify. But if you use the probabilistic method, you see there is a mean, there is a standard deviation. So you can quantify that much variation is there. Okay, so this is the mean and this is the deviation. Okay, so this can be done, this finite element model updating and the incorporating all the measurement and modeling error using the Bayesian probabilistic method. So what are the advantages of Bayesian probabilistic method? It can take into account of all the information that are available. Like it could be field observation, means measurement. It could be engineering judgment, means your own experience or someone else's experience can be incorporated as a prior information. Okay, so all those things can be incorporated into the model. So that is called data assimilation or assimilating data. Okay. Another thing is that it can handle non-uniqueness in the solution. Why non-uniqueness? Because it is an inverse problem. From the response you try to identify the parameter, right? So this is an inverse problem. Now if you perform inverse problem from a limited data, limited observed data, then there is a chances of getting many solution. Okay, because many other model can have the same solution. So which one to choose? Okay, so non-uniqueness is there. So that is also because of the ill-posedness of the problem. So that can be taken care by Bayesian. Okay, then you can also, of course, quantify the uncertainty. You can quantify the uncertainty, means you can update your prior information, whatever. Suppose you have the numerical model, so stiffness parameter are there in the numerical model, or material property like mass density is this much or stiffness is this much. So you want to update those things, right? So once you update it, then also you can quantify what is the error or uncertainty in the updated parameter. Okay, so that is the beauty of Bayesian model updating. You can quantify and also it can be done continuously, real time, because as soon as new data are available, the same process can be repeated. So you have the period, you have the observation, you are updating that observation or knowledge based on the based on the observation, then you get updated information. Then this updated information becomes your period for the next step. Again you are having some observed data and that keeps on updating. Okay, I will discuss this in more detail in the next slide. So this Bayesian method was proposed by this mathematician, which was a British mathematician, Thomas Bayes. Okay, so he wrote an essay on the treatment of uncertainty. Okay, and the original Bayes theorem was incorporated in that essay. Basically, he did not write Bayesian method. Okay, that time he wrote an essay, and this method was there, and then later the researchers found it very interesting and very powerful method, because it helps us in a situation when there is a measurement and there is a numerical model. Okay, so this type of thing is there not only in civil engineering problem, could be in medical science or any other thing. Okay, some prior information and some observed knowledge. Then you try to refine that information. For example, very simple way, suppose you want to visit some unknown location, okay, that you have never been to. Then what will your prior information? Your prior information is anything written in the website about that location, or you heard from someone else, right? You heard from your friend who has visited recently there. Okay, so that is your perception, right? Your prior information. Then once you visited that location, okay, then you get to know about that place in more detail. So that is your kind of observation. So the information or your knowledge or understanding about that particular place will improve further, is not it? So that is the basic fundamental of Bayesian method. So suppose you have a numerical model of a bridge, then you have some measurement from the same bridge when it is constructed. Then you try to update your initial model that is based on design parameter. Of course they will not match because of the discrepancy. So that updated information could be regarded as updated probability, or over here. So theta over here in this equation is the uncertain model parameter. It could be any stiffness, it could be mass parameter, it could be damping parameter, it could be some parameter like bearing stiffness or some other thing. Whatever you are considering as uncertain means not matching with the actual structure. Okay, that is the theta. So you want to update that based on the measurement from the real structure, is not it? So D is the observed data. So in this case, what is the observed data? It could be acceleration, or it could be modal parameter identified from the acceleration. Okay, if you want to update your stiffness parameter, mass parameter based on the modal parameter, that is also okay. So D becomes modal parameter, theta becomes your uncertain modal parameter, stiffness or some other thing. Okay, and this is called prior probability density function, probability of theta condition over C, and this is called probability of D condition over theta and C is called likelihood function, because this is based on the observed data. Okay, and this is on the left hand side, this is called posterior or updated probability, because now you are having updated information of theta based on the observed data. Okay, and this is called probability of D condition over C is the evidence, which is at the numerator. So if you perform the model updating of theta, then this does not play any role, except because this is independent of the theta, and it only ensures that integration of the probability should be 1. Okay, so this is constant basically. Evidence is constant when you try to update theta, okay, based on observed data. But if you want to also identify C, C is a model class. What do you mean by model class? Model class is basically, suppose I gave one example now. There is a beam, simply supported beam. You are modeling it. Either you are modeling it by Timoshenko theory or Euler-Bernoulli beam theory or some other three-dimensional non-linear geometry or some other method. Okay. So what is happening? Depending on the assumption and complexity, desired complexity, you can have different type of model, right? Simpler model, intermediate model, more complex model. So C is the model class, means it is the model among the defined choice of model, possible model, right? So C basically your particular model that you are considering. Suppose you are modeling by Euler-Bernoulli beam theory, neglecting many things like shear deformation is neglecting the large deformation. Okay, so that is your model. Okay, C is then your that model. But suppose you have a observed data of that beam, but you want to identify what is the best possible model that could fit the measured data, right? So basically Euler-Bernoulli beam theory is having some limitation. So that may not fit well to the observed data because it is a simplified model. Now we have a complex model, three-dimensional something is there. Okay, non-linear geometry and any other thing. Then that model could fit well with the observed data. So that process of identifying the most suitable model is called model class selection. So that is defined thing, and also finding the optimal value of theta is also defined thing. So both can be done using the Bayesian probabilistic method. Okay. So if you do only the identification of most probable value of uncertain model parameter theta, then you have to use this equation. So the model uncertain model parameter could be many, not only one, it could be many. Suppose there are many members and you are suspecting that you are not having actual value of stiffness parameter for those members, then your theta will be a vector. Okay, so this is given as theta j equals to nj multiplied by 1 column vector. Then you have a model, you can have defined model from a set of plausible model. Okay, and then observed data, of course not only one observed data, you can take measurement continuously or at a certain interval, so you can have many observed data set. Okay, so this is one observed data set, and also in all observed data set there is a number of sensors. For each sensor you will have one data. So if you have multiple sensors, you have multiple data. Okay, so that thing is taken care in the observed data set D. Okay, so this, as I said, the Bayesian probabilistic framework could be used for both the purpose. One is parametric identification, that is the understanding or evaluating the updated uncertain model parameter based on observed data, and another is the model class selection. Okay, C, which is the best fitted model. Okay, so let's try to understand all of these. First is the prior PDF, probability of theta condition over C. So it is the prior PDF, means any information, right? As I give an example of visiting a new location, na? So information that is available to the site, you can have YouTube video of that location. So that is your prior information. You can hear from your friend, that is your prior information. For such a Healthmonitoring problem, suppose you have a finite element model developed in Abacus or MATLAB or Python, whatever it is. Okay, so that is your prior information. So then you try to update that thing based on the observed response. So this, how to represent this? So this can be represented as a two-way. One is improper prior. Improper prior is uniform prior, means you are not assigning any distribution. Uniform distribution means suppose you are tossing a coin. Okay, what is the chance of getting a head? Okay, after it is landing. So if you don't assign any prior knowledge that of course this coin is relatively biased, kind of, it will always tilted in some other way, so it will fall on head side. Okay, suppose that biasness is there, but you don't know. So you are not assigning any prior information. You are giving 50-50 kind of thing. So that is uniform, means you are not assigning any prior biasness to the problem, right? So that is one way. Another is the, suppose you have tossed it for several times previously, and you have found that out of 10 times, at least 7 times, you found that it is head. Okay, so you can use that information as a prior that it is having the probability of 70% of chances that it will fall on head side. Okay, so if you use that information, your updated information will be more accurate, right? So if you don't use that information, then probably your initial guess or based on the measurement will be slightly deviate from the actual thing. Okay, so prior information is very important. Your initial, it is kind of your initial guess. So if suppose you are making a finite model that is totally irrelevant or deviate very far from your actual structure, then what will happen? Your model prediction from that model will be erroneous, not accurate, because it is largely differentiating with the actual system, right? So whatever you are getting response from that system is not correct, right? Natural thing, right? So what you want to do? You want to have a system or finite model that is highly accurate. Okay, so you will make initial guess that is very close to the actual structure, not exactly close but very close. Okay, then based on the measurement you try to update that structure so that eventually the prediction from that model matches exactly with the actual response from the structure. So that is the goal. Okay, nothing else. So so this is in mathematical term, conjugate prior distribution could be used. Conjugate prior distribution is that suppose you are assigning a distribution for the prior. Usually we use Gaussian distribution in most of the cases because it is mathematically very easier to model, and also very many natural phenomena also follow the Gaussian distribution. So prior distribution is Gaussian, and your likelihood if you also Gaussian, then what will happen? Your posterior distribution will also be automatically Gaussian. So in that case it is called conjugate prior distribution, when the updated posterior distribution is also same as prior distribution. Okay, right? So then there is this term probability of D condition over theta C, which is the likelihood function. So this actually expresses how probable the observed data set is for defined setting of parameter vector theta. Means how your model prediction actually matches with your observed data set theta, that is governed by the likelihood function. Okay, so this actually correlates between the model prediction and the response from the structure. So basically it is minimizing the error term between the model prediction and observation. Okay, how it is doing that will be discussed in subsequent slide. And then there is another is evidence. Evidence is nothing but the normalizing constant in case you are doing parametric identification, because it is independent of theta. Okay, it only ensures that integration, because always when you discuss about the probability density function, the area under the probability density function should be 1, right? So it ensures that only. Okay, if you want to evaluate this model selection, that means which model best fits the observed data, then you have to go for this multi-dimensional integration. Okay, you have to evaluate this. Okay, this is called then evidence. You have to evaluate. That is very complex problem. Okay, so those who are working on this field could understand this terminology. So posterior distribution is what you can see over here. This is the likelihood, means observed data, and this is the measurement noise kind of thing. Observed data is also not accurate now, as I said, so there is some deviation. Then this is your prior information, and this is your uncertainty in the theta, uncertainty in the theta. Okay, so then you want to update this so that your posterior aligns closely with your likelihood or observed data. Okay, so that is your goal. Okay, so that is a simple illustration that you need to achieve. So this is continuous process, so you have to do it rigorously and continuously. Okay, so this is the model class selection algorithm. So in case of parametric identification, you will be using only this formula, because this becomes kappa 0 is this evidence 1 by P of D condition over C, that is constant, so you don't have to evaluate. Okay, you can write it as a constant. Only thing that is you need to evaluate is period information, period PDF, and posterior this is likelihood function you need to evaluate. So in case of health monitoring problem, I will discuss how to formulate this too. Okay, so another question that I want to ask you, that model complexity and base model selection. Now as I given several examples, that Bayesian probabilistic method can also be used for model class selection, means selecting the best possible model that is fitting the observed data. Now I have a question for you. Do you think that a more detailed model is the best model? What do you say? Very complex model, that is the best model? Suppose you have developed a very complex mathematics, some large equation to predict something. Okay, so do you think that will be your best model or some other? Okay, yes. So answer is no, basically. Yeah, you want to say something?
Depends what outcome we are getting. Is it relevant or relevant or not?
Slightly correct, yeah. So basically it depends on the observed data, not only the model, because you want to fit the observed data, no? So it is not necessarily that your best model or more detailed model or complex model will fit the observed data. Okay, so for example, there is a graph over here. So C1 is the simplest model and C3 is the complex model and C2 is the intermediate one. Now I want to fit this observed data D0. Okay, so which model among these three will fit this observed data in a best possible way? What do you think? Yeah, that is correct. But first try to understand why the simplest model is looking like this and why the complex model is looking like this. Okay, first you try to understand. So this is probably density and this horizontal axis is data, observed data. Okay. Now this is flat because more complex model means more data it can fit, wide range of data it can fit. More complex model, so from very simple data to large kind of data it can fit, wide range of data. So there is a large variability in the best fitted model. Okay, you can expect large variability. So what happens in the best fitted model? Because of the large variability, it assigns relatively smaller probability to a particular set of data, right? Because it has to take care of wide range of data, so it assign, or when you get the model prediction from the most complex model, you are not getting similar kind of result, right? You are getting sometime observed data is like this, sometimes observed data is far away like this, because it is having large variability and complex. Okay, so model prediction is not kind of similar, right? That's why it assigns very less density to a particular set of data set. That's why it is having flat. Now for simplest model, what is happening? Simplest model, you are having fairly similar data set you are getting, because the model prediction is same. Okay, whatever you are giving input, it is giving you same kind of outcome. Okay, so they are there in a very confined space. Okay, so therefore density is quite large because they are not varying. Okay, variability is less and all the prediction is fairly similar, so density is high. So that's why it is quite sharp. Okay, and it is flat. Now if you talk about D0, then what is happening? C2 model is the best predicted model or best fitted model for this type of data because it is lying in this area for which evidence is high for C2. Of course, for C3 it can predict or it can model D0, but the evidence is up to this only. Yeah? But for C2 it is that much. For C1 very complex, very simple, so it cannot model D0 at all. Okay, so best fitted model is here is C2. So remember that it is not necessarily true that a more detailed model is the best fitted model for a particular set of data set. So you have to rely on the data set first, what data set you want to fit, and based on that you choose a model wisely. Okay, so that process is called model class selection using Bayesian. Okay, so we will not discuss model class selection today. We will discuss only parameter identification or updating the yeah. Yeah. No, suppose C2 is the intermediate model, not the most complex. Okay. Most complex is C3. Yeah. Yeah. No. You see now, here is this graph. This is the evidence of C3 model. Okay. So C3 model can fit wide range of data. Yeah. For example, if I ask you to fit this data set, suppose it is lying over there, then probably C3 can only fit. C2 cannot fit, C1 cannot fit. Because C1 is the simplest, C2 is also the simplest, means slightly more complex, but it is also simpler than the C3. So in that case, for this data set, probably the right choice is C3. So it depends on the data, where data is lying or what type of data you are fitting. Okay. So based on the data, you have to suppose you think about any data set. Some data set are contained in a particular portion. So fitting of that data is much easier probably. Suppose you have a very complex data. Okay, then probably you need to have a non-linear kind of curve to fit all of those data. Okay, so very complex model is needed. So it's based on data, what type of data you want to fit, you have to judge a best fitted model. Okay, so based on the data only, not any other. Okay. Yeah.
We have more number of variables.
Yeah, yeah.
That's why more non-linearity is more.
Yeah, yeah. Of
So
course.
we have to see the sweet spot. Like it is not very simple.
Yeah.
It is not overfitting as well.
Yeah, yeah, yeah. That's why I said you have to look into the data only. What data you want to fit. Suppose, as I said, all the data are like this, lying along the straight line. Then you will choose y equals to mx plus c. That will fit the simplest kind of model can fit those data in a more accurate way. You don't need very complex like y equals to mc to the power q plus something some power of x, right? You understood? So you have to check the data, what type of data you want to fit. So based on data you need to choose the best possible model. So that Bayesian framework could help you to identify. Hmm.
Data set is small.
Yeah, yeah.
If someone is using complex model,
Yeah, that will increase computational demand as well.
but what about the accuracy?
Accuracy, as I said, for this data, you will get C2 will be most accurate one because the evidence for this model is the best. Okay, so even if you use the complex, that is why I am saying that this is not the best fitted model for D0 na. So if you use most complex model for fitting this data, you will get erroneous result. You take simple problem, you just have the you generate the data, okay, by using some, suppose there is a straight line equation y equals to mx plus c, you add some noise and scattered data you generate, then you try to fit that data using a very complex model, then you see the error and then you check the error for y equals to mx plus c. So you will see the simplest model will be, for example, this if the data is lying over here, which one will be the best fitted model? C1. Okay, so it's best, yeah,
Bias variance
yeah,
trade-off.
yeah.
Like if there is a structure we are going to model,
Hmm.
medical model is to be performed. Like if we are catering pessimistic, being pessimistic and we are modeling, then it would be likely to called as B. And if we are more optimistic, then it would be called as C1. And then if we are most likely to happen, that would call C2, isn't it?
For the structure health monitoring problem, what you need to do, suppose you have very limited data, right? And you have, you can of course have numerical model, you can have very complex numerical model. Then what will happen? Your number of degree of freedom, number of element will increase, very increase. Then you will have a very lot of ill-posedness problem is there, because you are measuring response at a particular point, only few point like 12 point or 10 point, and try to update the entire structure which is very large. So in that case, then the problem will be ill-posedness of the problem will appear. So what you will do, you will make your numerical model more simpler. So instead of like cell element, you can use beam element, or instead of solid element, you can use cell element. Depends on your purpose or study, right? So I can have very complex model also that is needed for probably simulating stresses or some kind of other study related to local response. So you can have very complex model, very accurate model, okay? But for global vibration, you don't need a complex model. You just model it using beam element, then you can get similar kind of data, okay? So you have to trade off. This is a trade off between the what accuracy you want and how the model is fitting. Yeah. Of course, I am not discussing here the computational time, but the more complex model generally takes larger time to execute. Okay. Yeah. Yeah, that is generally because it is simple. Yeah. Suppose you want to do a, yeah, I agree with you. Suppose you want to do a, yeah, 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 exactly true.
But for C1, I think for trading data, like what data we have had, we have measurement. C1 will be too simplified, like it will not be applicable.
Suppose you want to do a preliminary study, you have very limited time, you want to do something, okay, you have to tell something based on very limited time, okay. So then you will choose a simpler model, and suppose in system identification also, suppose there is a measured acceleration, I want to determine the natural frequency mode shape of structure quickly. Then what you will do? You will use simple method like FFT. Just do FFT and you find the peak and tell the. So that is kind of very simple way to tell the natural frequency. But that might be incorrect. Okay. Then you have to go for complex procedure like SSI, ERA, and then the noise removal. So you have to plot that stabilization diagram. Okay, you have to screen out the unstable mode because of the noise. You have to keep only stable mode. So there are many things. So this is a simple demonstration on whether the best fitted model can fit all type of data or not, or whether the best fitted or the more detailed model is the best model? Okay, the answer is no, of course, because it depends on the data. Okay, so if data is very simple kind of in nature, it is not varying too much, then why you need more complex model? You need a simple model to fit that data. Okay, that is the answer. Okay, so because time is limited, I have to move on. So today you are asking too many questions. Why you did not ask in other classes also? Okay, yeah. Okay, so of course this has been discussed already. Now application in structural health monitoring. So I have discussed this thing from the viewpoint of like as a mathematical tool which can be used for any type of engineering field. Now if I apply in the field of structural health monitoring, because this is the sustainable structural health monitoring course. So what is happening? A system is characterized or defined by a stiffness parameter or model mass parameter theta, right? Once you define the stiffness or mass, then you define the system. Every system has defined stiffness, defined mass, right? So then suppose there is a excitation, known excitation Ft is there. You are applying a known excitation to a system. For example, you assume a beam, okay, simply supported beam. So you can model the beam using the theory, matrix analysis or FEM, whatever it is. Then you are applying some known excitation. So from that beam you will get the prediction xt, model prediction, right? So that is your model prediction coming from the numerical or theoretical model, right? On the other hand, suppose you construct that beam on lab, okay, then from the beam you can have, if you apply similar force on the beam, you will get some response. So that is your observation ynt, okay. So now there is a relationship between the observation and model prediction. So they are related. So your model prediction, first try to understand your xt is depends on what? Your xt is depends on the input force, what force you are applying, then your initial condition, what is the initial condition of the beam or bridge or structure, then your model parameter. Of course, that actually defines the structure, whether it is stiff, whether it is flexible, whatever it is, okay. So based on that, your model predicts response will come, okay. On the other hand, from the observation you have data, and from xt you have model prediction. So of course they will not match. Whatever model you are having cannot exactly represent your actual structure because of some deviation, right? So that is called error. So this error is we are calling as a prediction error. So this prediction error could be additive, could be multiplicative. If you assume additive, then it is a addition of that modeling error because of incorrect assumption that we are making while modeling the numerical model, and it could be because of the incorrect sensor data. Sensor could have some noise also. Also there could be ambient vibration. So there could be measurement error also, right? So what we need to do, this we want to minimize, this prediction error we want to minimize, right? So that your prediction from the model could be enhanced, could replicate your actual behavior. So how to do it? So this can be done. So this is coming from the difference between the measured means observed response and the model prediction. Okay. Now why we are using this L0? L0 is there because in the theoretical model or numerical model you have the information for all of the degree of freedom, right? But in the measurement, suppose you are putting sensor at few location, so you have only measurement at few location. So you have to correlate between these two. You cannot compare the measure response with any other location, right? You have to correlate with the same location of the theoretical model. So that correlation has to be there. So that correlation is taken care by observation matrix, okay. So this equation that you are getting by just integrating it into the Bayesian framework, that is the updated PDF of theta, and you have to maximize this Okay, so instead of maximize we will do minimization. Why? Because these are exponential. This is also, if you represent, as I said, Gaussian PDF. If it is Gaussian PDF, then you know the formula of Gaussian PDF. Half of 1 by square root of 2 pi sigma square. Then it is exponential of minus something, right? So if you eliminate the constant part and take the negative logarithm or logarithm and then take negative, then it becomes a minimization problem because of negative is there. Okay, so this can be minimized. So in terms of structure health monitoring, let me tell you. So what do we have? Any dynamic system is prescribed or characterized by this Eisen equation. That is K multiplied by the mode shape equals to omega square, means modal frequency squared, then m and phi r. That is well known Eisen equation, right? So here we are writing K as a function of theta. Why? We are considering K as an uncertain. Okay, theta is the parameter that we want to update. In the case of mass, we are not writing because we are assuming that mass is accurate. If it is not, then you have to also write some function. Okay, then you have to also update it. Okay, so what is happening? If it is a linear system, this k theta can be represented by k naught plus summation of this theta multiplied by ki. Do you understand this thing? These are k naught and ki, all are constant. Only thing is variable is theta. Suppose you are predicting that material density E, modulus of elasticity E is not same between the numerical model and the actual structure. Then you want to update E. Okay, so the theta will be E. So whatever else that is there in the stiffness matrix is kind of Ki. Okay, or K naught also is depends on how you are representing the equation. Okay, so then your posterior PDF is obtained by just by substituting this equation, means this is the likelihood function for the modal frequency and likelihood function for the mode shape. So basically likelihood function is the difference between the numerical prediction and the observed response. So likelihood function of mode shape means natural frequency means it is the difference between the natural frequency predicted from the Van der Waals model and your observed natural frequency from the measurement. Okay, and same goes to mode shape also. One of the equation that is mentioned over here for the mode shape. So psi r, this is the observed mode shape coming from the test. Then these are the mode shape component coming from the Van der Waals model, right? So I have introduced L0 to just correlate that it is the mode shape component corresponding to measured location, okay, right? So then there is a measurement error or prediction error over there. Okay, so you have to model this using Gaussian. You can model. Okay, so that will give you this type of equation. You see, this is the difference between the square of the natural frequency. This is the observed. This is the model prediction coming from the model prediction. Similarly, this is the mode shape coming from the observed, and then this is the mode shape component coming from the model prediction. So then you just minimize this and get the your updated theta. Okay, by minimizing this equation. Okay, this is very looks very complex but not so difficult. Okay, if you learn Bayesian, it can be easily incorporated. Okay, so now how to solve this equation? So I have obtained this probability, updated probability of this uncertain model parameter theta. Now I have to identify the mean and standard deviation of this updated probability, right? Because it is a probability density, it is quantifying the uncertainty. So I have to identify the mean with most probable value of theta and its uncertainty, right? So I have to solve this equation, no? Okay, get the theta. So this can be very tricky for non-linear problem, but for linear problem you can have a closed form solution, because linear problem you can represent this observed, if it is Z, suppose observed response is Z, then it can be represented as H multiplied by x. X is here uncertain. I should have represent by theta only, because here I change the abbreviation of the parameter. Okay, so here x is the uncertain parameter. So here it is a linear system. I can easily write observed equation like this, and this is the period equation where there is a definite mean of the period and there is some uncertainty in modeling error. Okay, so then this objective function is like this, which is the theta minus theta bar or x minus x bar here, and then this is the observation coming from the likelihood function. Okay, the difference between the observation and the model prediction hx. So this can be minimized. You have to maximize the posterior or minimize the objective function. Okay, either way, because this is the negative logarithm of the posterior PDF, you have to minimize. So you have to do dj by dx equals to 0. Simple optimization problem, that if we have to minimize or maximize a function, then partial derivative will be equals to 0. So if you do that, then you will have a solution for x. Okay, what is the solution? X bar means mean or updated, most probable value of updated theta, or x is equals to this mean, period mean, plus this function. Okay, where P is the covariance matrix. Covariance matrix, from covariance matrix you get the standard deviation of that uncertain model parameter. Okay, so this is a very interesting equation and largely used for linear inverse problem. Okay, this is called linear or Bayesian linear regression. Okay, so we often use this problem because most of the cases our system is linear. So if it is non-linear, then the solution you have to obtain by using the simulation based technique. Okay, you have to draw samples from the posterior PDF. Okay, like this. So sampling based algorithm will be used. What type of sampling based algorithm can be used? MCMC method, there is a Markov chain Monte Carlo, or Metropolis Hankstring, or Gibbs sampler is there. So what they does, they basically draw a sample from a this type of proposal distribution. You assume a proposal distribution because you have to evaluate that posterior distribution. Now you are assuming, because Gaussian distribution, if you assume for period and likelihood function, then you can represent it in a closed form. But if it is non-linear, non-Gaussian, then your posterior PDF is very complex. You cannot write in an analytical way, analytical equation. So it is a multiplication of two probability density, period and likelihood. So how do I know which distribution it is following? No answer, right? So what I need to do, I need to draw sample from a assumed distribution, or which is called proposal distribution. You assume a proposal distribution, draw sample from it, then you try to run like this kind of probability of acceptance, which is given like this. Okay, so in the illustration, kind of you start with a chain. These are the kind of Markov chain, series of samples. Okay, so you start with one and go to next and next and next. So how do I go to next? When it is going to next, first it will check the acceptance criteria. If it is fulfilling that acceptance criteria, that is the probability of acceptance is less than 1 or this value, then it will be accepted or it will be rejected. Okay, that sample will be rejected and it will go to the next chain. Okay, so you can follow this illustration. So initial sample, then it is going to next, then calculating the acceptance criteria. So if it is less than 1 and of course it is this ratio of this, then it will be accepted. Otherwise, suppose here it is going outside, so more than 1 or something like that, so it is rejected. So that way you draw a lot of sample. Of course you can, initially you can reject the burn-in sample, because to come from here to here or populate this middle part, you may need to burn initial 500 sample, 1000 sample based on your problem. Okay, so then you reject, those are called burn-in, means the code is running and it takes some time to come to its code. Okay, So you will reject those, and then you will only preserve those sample, and whatever you draw the histogram kind of thing, and you will get the posterior distribution. So that is the only way to calculate the posterior distribution if it is not having any definite mathematical terminology, okay, or form, okay, right. So time is very limited. I think I have crossed almost. So let me discuss this in terms of practical implementation, because GAN has also suggested to whatever you are teaching in GAN course should be correlated with the practical implementation. So I will briefly discuss how I can correlate this with the structure helping of real life structure. So this was the bridge in Japan, very old bridge, truss bridge, okay, constructed in 1965. So probably he is working on this bridge, or probably you have studied this bridge, right? So then this is the numerical model developed in MATLAB, the same model of this bridge, but in developed in MATLAB. How? Just you write basic coordinate of each node, then connectivity of the member, okay, how they are connected, and then you just plot it in 3-dimensional, okay. So you will easily get this model, and of course you can form the K matrix, A matrix, then your fundamental model is complete. And to form the K matrix and A matrix, you need this information. E you need, mu you need, G you need, okay. So this model is having this much of nodes and this much of element, and this is the degree of freedom, okay, total degree of freedom. So we carried out some measurement like accelerometer, okay, on the deck, on deck level, okay, because we want to identify the global mode shape, okay, not local, global mode shape. Now of course there was another sensor at the local diagonal, okay. That was the tension diagonal member, okay, for this type of bridge, okay. Then you run a car run test, means of course you can have ambient vibration also. These days you can use ambient vibration also to identify the modal parameter. But if you run a car run test, means you are simulating the response by running a heavy truck on the bridge and then measuring the free decay, free vibration response of the bridge. So that is ideal kind of response for system identification, because that response contains only free vibration of the bridge. So from that response you can identify the modal parameter related to bridge only. So if you identify from the ambient response, there could be possible that there are lots of noise, okay. So you have to segregate the noise. So that is challenging. That is the challenging task. So what I did, we run a car run test like this. Vehicle is going from here and there, and then these are the response due to vehicle movement. So you see, if you crop this, if you check the video of traffic, okay, recorded during the measurement, when the vehicle has passed completely the bridge, and then there is a free decay. You can see exponential decay. Those who are from structural dynamics can understand. Because of the damping, it will decay like this, e to the power minus j omega nt, right? So you can see this decay. So extracted from free vibration response, you can do system identification. So this type of modal parameter you can identify, okay, using the SSI ERA, and of course from the MATLAB also you can identify these are the vibration mode and these are the frequency. Of course there are discrepancy between these two because of our initial assumption is not so correct, okay. So you have to update this so that your final model matches with the actual response of the structure, is not it? So this can be done over here. You can see the updated mode shape using the Bayesian method. I am not discussing the methodology again because there are lots of equations. So you can go through the paper, you can get those equations. So these are the measured mode shape and the theoretical updated mode shape. So they are not overlapping, they are overlapping with each other, and also you can see now the measured frequency matches with the updated frequency, okay, or updated frequency matches with the measured frequency, okay. So there also I have tested the robustness of algorithm against the various level of noise. So as you increase the noise, there is some discrepancy started to appear. Okay, so up to certain level of noise, so if there are too many noise in the data, then probably your methodology will not converge. Basically it is convergence kind of thing. Okay, so you are updating the model and finding out the optimal value of theta, which represent the best possible response from the structure. So up to 10% of covariance noise, it could detect or it could update the frequency accurately. Then probably probability of damage can also be calculated using this equation. There is a equation where you introduce a damage factor D, and then using this equation which actually uses the updated theta corresponding to the damaged structure and undamaged structure. Okay, or you can say two different measured time. Suppose you are performing measurement this year and then updating the model based on measurement this year, then after next year you went there at the site performing the measurement and again updated your model, and then you correlate these two theta. Okay, if there is a changes between the updated theta and their standard deviation, then you will see there is a peak in the or there is some kind of damage probability will be detected for certain damage index. Okay, so this is done by numerical simulation, because in this bridge for the first span there was no damage. Okay, so what we do, we have introduced some simulated damage, 50% reduction of one of the member, okay, in stiffness, and then you identify the modal parameter or evaluate the modal parameter. Then you add some noise also with this, so that it reflects the actual measured response. Then update the another baseline model using that data. Okay, so then you check this. So you will see there is a damage that could be detected using this formula, but this is based on simulation. Okay, so that has to be verified with the actual response. So in the fourth span of this bridge, there was a actual damage that was there in the lower end of the diagonal member. So, and these are the, because it was a measured damage and one of the diagonal member, so that needs to be treated or corrected in quick time. So that time we had measurement with only two sensors, so that the measurement could be performed quickly, and then subsequently the retrofitting or reinforcement of that damaged member could be done. So this picture shows reinforced condition, this picture shows damaged condition. So you see, once this system modification was performed based on this data, these are the damaged natural frequency, these are the healthy natural frequency. Okay, means reinforced condition. So you see there is no much difference between the natural frequency of the global mode. Okay, because of the damage. Of course, in the diagonal mode, because we have placed sensor over here near to the diagonal member. So in this case we knew the damage location, so that's why we place the sensor there. So in the real problem we don't know where the damage is, so we will not place sensor over there. Okay, we will place the sensor only the global deck level. Okay, so you cannot identify this diagonal mode unless you place the sensor over there, right? So our objective is to identify the damage based on this mode, okay, global mode, not on this mode. So that is the challenging thing. So here what we have seen, because of this damage there was no change in the modal frequency of the global mode, whereas there was some changes in the damping was observed. Okay, so those will be probably discussed in the next session in the afternoon, because we have crossed the timeline. Okay, so I will discuss. So I am ending here. If you have any question, we can discuss quickly, or maybe in the next half. Sorry, GNB. What is the full form? GNB. Gaussian naive Bayes. It is kind of one type of optimization problem. Now that saying that so this is one variant of this type of thing, like Kalman filter or other things. Okay, similar to things, but I have not done any work on this. Okay. Okay. Any other questions related to structure recording? Okay. So we will stop here.